All right, recording is rolling. It is Wednesday, January 24th. Today and tomorrow, I want to do a couple labs with you guys. We end up switching. We're going to do speed of sound lab today, partly because I think it fits better with the schedule. We got these slightly shortened classes. All right. Other stuff. Here's a rocket launch after school, 511. If you want to see 3 astronauts head to the International Space Station, look for that then. Reminder too, Max has a survey going, so if you want to help him with AP capstone research, that link is on Google Classroom. Okay, so before we get to this lab today, got some time to do another question. I threw at you guys yesterday, right? Threw you guys a question yesterday. I said to answer it today, so we're about to do this. It involves a spring. Tomorrow, there's going to be a lab that looks like, oh, here it is. Okay. That involves going to take the spring, say like hang it from a hook, hang it vertical, put a, let's go this guy, throw a lab weight on it, right? And something to do with it stretching, right? Now, so it might look like this. Say I got the ceiling, right? I got some springs hanging from hooks. Look on the ceiling. Got these springs lined up. All good. Okay. And let's say it starts off with some like unstretched length. If there's no weight on it, I'll find it good. Okay. Then I'm going to take the slab weight and let's say I hook it on that one right there. Okay. And I slowly lower it until it reaches an equilibrium position. Let's say it stretches, this far. Okay. I'll call that stretch amount X sub A, right? So I just hang the lab weight, right, and slowly lower it to equilibrium, right? Oh, hence equilibrium, right? This might be good for your notes, by the way, if you got notebook out. Okay. Or maybe you let it oscillate after a few minutes and eventually comes to a stop and would also stop there, right? Versus, what if instead, look at this, maximum stretch, right? And guys, look for this terminology if you see this particular setup in an AP question. This could be a multiple choice question. This would also be a completely fair FRQ. I'm about to do a whole set of derivations here, right? What if I take this and I hook it right there, right? Everybody look up here, look right there. And then I just drop it. And do you think it's going to overshoot this equilibrium position? Yeah. Like way down here? Yeah. And then when it does reach its maximum stretch position, where do you think there's more force? Weight pulling down or the spring pulling up? Spring pulling up. Do you think it's going to oscillate? Wow, 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 right? It would oscillate something like this, right? No, eventually it'll settle into this position. Oh, yeah, go ahead.
Isn't there also the chance that you just break it?
Well, yeah, besides that, right? Okay. Yeah, so we're doing like besides, yeah, we're ignoring all the like air drag and non-ideal spring. Yeah, so we're making a bunch of assumptions, including ideal spring, which means that regardless of how much you stretch it, it has the same spring constant. It's going to follow Hooke's law, for example, there, right? So maybe it stretches like down here, for example. Okay, let's make some little hook right there. Right. And so the same mass, right? So mass M, right? But this stretch distance, I'm going to call X sub B, right? And question is, what is X sub B compared to X sub A, right? And there is a ratio that is pretty much a universal answer as long as you have an ideal spring, right? And the same weight, blah, 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 right? Okay. Before I go driving this, does anybody know what the answer to that question is? Huh? Where? Wait, somebody said it. Two to one ratio? Two to one ratio? Right. So for example, if XA was 5 centimeters, XB would be 10 centimeters, right? Because it'd be twice as much, right? Right. So let's actually prove that with physics equations from, how about from last semester? I think you can solve this, right? Now, equilibrium. Guys, what framework do you use for equilibrium? It's not. How about, guys, if something's in equilibrium, what can you say about it? All the forces balance out. All the forces zero out, right? Right? Yeah, you guys hear at it? All the forces zero out. So here, if you draw a free body diagram, does this have a weight pulling down? Call it mg. And is there a spring force pulling up? And I could call it spring force. I call it kx, like from Hooke's law, F equals kx. Okay. And those two would be balanced. So here's my framework right here. Like if AP asked you to solve this, especially in FRQ, they'd want to see all your steps. Your first step would be this. Say, well, I'm going to use the sum of the forces goes to 0 newtons. Right? That's my framework for equilibrium. I see equilibrium, sum of forces goes to 0. Right? If you like, you can throw a little subscript y on the force because it's all vertical. Right? So something to do with, and this would be subscript a on that x. That's what it would be, right? So k x sub a minus mg goes to 0 newtons. And if you solve for x sub a, that'd be, see, this weight divided by k, so it'll look like this. How far it stretches is the weight divided by the spring constant. Okay? There you go. That's how much it stretches for equilibrium. Equilibrium, right? Nice, just hang on. Okay, now let's do the maximum stretch. Guys, maximum stretch, what framework do you use? And it's not forces, it's what? Energy. Energy conservation. Okay, we're going from like point A to point, or maybe we should say point 1 to point 2, and we're going to do energy conservation. Okay, I'm going to treat this as a block, spring, earth system. Okay. And the fact that I threw the earth in the system is maybe a hint as to how it's going to set up. Okay. Because I made the point the other day, like, even if this was turned horizontally, then it would still oscillate the same. Okay, but besides that, I'm looking for maximum stretch. So now Earth's gravity field does matter, right? Like if this was on a different planet or on the moon, it would probably stretch differently, right? Okay. So we're going to use this framework right here. Sum of energy at the top equals sum of energy at the bottom. Right? So separate that right there. Right. So guys, what kind of energy right here? What type of? Gravitational potential energy. Right? Well, if I have some kind of MGH, I better define some zero height. I'm going to call this dashed line right here height 0, right? Just like the lowest point, or I guess like maximum spring stretch. Right? Now, if that's height 0, height is 0 meters there. I'm just defining the lowest point, which is a common thing to do. Then wouldn't this original height be just x sub e? So gravitational potential energy is that MGH, right? Except instead of MGH, I'm going to write MG x sub e, because x sub e is the original height relative to where it ended up, right? And I'll say equals, and then by the time it gets down to here, well, now where'd all the energy go? Into the spring. And what's the expression for that? 1/2 kx squared. A little subscript beyond that x. Because that, hey, is that the same x? X sub b, same one, right? Are you guys okay with that setup? Wait a minute, am I leaving something off? Ooh, what about kinetic energy? Do I need kinetic energy? Yeah, you're right. Yeah, you guys hear Steven. There's no kinetic energy here or here. So we're done. That's it. That's the entire setup. There's it's 100% gravitational potential here. It's 100% spring potential here. Right? Now in the middle there's kinetic energy, but we don't care about the middle. All we care about is the beginning and ending. Ooh, can I divide through one of these x's? Right. Cancel out. Okay. If we solve for the remaining x sub b, say cross multiply the 2, divide down the k, x sub b is 2 mg divided by k. There you go. Right. So that right there, this page, look, it's just a handful of steps. It all fits very cleanly on one page. That right there would be a completely fair FRQ question. Okay. All right, so you guys good with that? And look, this is 2 times XA. Look at that. Right. All right, so tomorrow's lab is going to look more similar to that type setup. So, all right, but let's switch over to this speed of sound lab.